So thank you everybody for being here today, and I want to thank the organizers. This is phenomenal. I've never been to this event before, but I appreciate all the work and the community that has gone into this. So again, my name is Kelly Henning. I am the COO of Stoke Space. I'm assuming most of you have heard of us, but just in case you have not, we are a launch company. We started off as a launch company. And so we're looking to develop rapidly reusable rockets. So we're looking to do that in order to be able to fly very, very often and reduce the overall cost of space. That will tie in a little bit into some of the discussions I have later. But with our second stage, fully reusable, that opens up quite a few other type of applications. For example, a down mass. So down mass is a very constrained market right now, bringing things back from outer space. There's only a couple of vehicles that can do that. But our second stage is uniquely capable of doing that. It wasn't necessarily something that we set out to do, but it is a very nice byproduct of the overall design. And with that, second stage being reusable and allowing it to bring things down, that opens up things for earth to earth or earth point-to-point cargo, which is rocket cargo, so rapid delivery of goods, or even lunar landings and bringing them back. So our second stage is incredibly robust, so it allows us to land in very austere environments and take any kind of debris or kick up, and it doesn't need a particularly large amount of infrastructure in order to do that. So that is Stoke Space, and that is our rocket Nova right there. Chris asked me not to be salesy, and I have to confess that it's been a while since I've done a non-sales presentation. So if you see it slipping in, I genuinely apologize. You could call me out on it though. Okay, so who am I? So just a note, all of my slides have background pictures from Stoke Space, and I'm far better if you guys are interactive and ask me questions. So feel free to jump in and ask any type of question that you may have. So as I said, COO Stoke Space. Before that, I was at Raytheon Intelligence in Space. Raytheon, when I was there, they wanted to create a kind of a rapid innovation center, very similar to Phantom Works or Skunk Works. So they came out with something called Department 22. I was the engineering executive, so I ran that for a very short amount of time. It was short-lived. They got rid of it very quickly. It was rather expensive. So I did that. And before that, I was at Northrop Grumman. Both of these are in Southern California. So Raytheon was in El Segundo. Northrop was in Redondo Beach. If you know anything about Northrop Grumman's history, you'll know that, yeah, I was actually hired into TRW, which dates me because I am older. So Northrop Grumman, I was there. The last couple of years, I was in strategy and business development, so any kind of technical strategy, those types of things. And I did that for a little bit. But before that, I was at TRW, and I was hired in as an RF designer. And so, and I'm going to spend a little bit of time on that because I think it kind of goes to my overall philosophy. So I was at the Rutgers University. I did my undergrad there. I went and did my master's at University of Michigan. I studied I studied electromagnetics, but most of my work there was actually done on RF MEMS. I know there must be some hardware people here, but RF MEMS are microelectromechanical systems, and so they're very tiny systems that move. And so they are notoriously unreliable. And so, and they're one of those types of technologies that seem like a very, very good idea, but getting them to work over and over again for many cycles is hard to do. And so every so often they become popular, and then they become unpopular, and then become popular and unpopular. And this happens every decade or so. However, I was studying them. I did EM modeling of it, which then translated to the power and where the power hotspots were, which we were theorizing which would go to the thermal distribution, and that would help us with overall reliability. So I studied that for a while, and I finished my master's. I needed to get a job, and I was lucky enough to graduate during the dot-com bust. Does anybody remember the dot-com bust? Yes. Okay. So at that time, right before that, you had a lot of startups. right after that, all the startups were kind of drying up, and there wasn't many places to work unless you wanted to go into aerospace and defense. And so TRW has a phenomenal RF design group. They do all kinds of very innovative things. They also have a foundry which develops microelectronics. So they are the state of the art foundry. They actually have the fastest transistor. So one that works at over a terahertz, and they designed that for a imaging system. However, they had just won a program called RF MEMS Reliability Improvement Program. And so DARPA funded this, and I'm sure a bunch of you have worked for DARPA or done work for DARPA. So if you haven't, DARPA is very cool. So when we think about the government and we think about them moving slowly and not taking risks, people are not talking about DARPA. So DARPA has a philosophy that if they're not actually failing often enough, then they're not trying hard enough and they're not pushing themselves. And so that's generally the philosophy that exists. And they've set up these contracts that are wonderful in the sense that it's best effort. So you have this problem, they put these crazy goals for you to solve, and it's best effort to see if you can solve them. And so DARPA had released this RF MEMS improvement program, and so TRW hired me in. And mostly I was hired. In this particular case were incredibly sought after. They have very, very low insertion loss. They have great isolation. They have low return loss. They almost use zero power to switch. And so they could be useful in many, many different types of systems, specifically phased arrays, which require quite a few switches in order to steer the beam. And so this was something that could be very useful if we could just get them to work. And so in our particular case, we were looking at a MEMS that had wonderful characteristics. However, it required over 200 volts to activate it. And if you're talking about a system that is about 200 square microns, you're putting 200 volts on 200 square microns, which is incredible. So they were looking for ways to increase reliability, but also reduce the overall actuation voltage. And so I was on this team. And I was specifically going to do the modeling of this MEMS, both the mechanical as well as the RF. And so they asked me, they said, okay, Kelly, we need to figure out, design, and simulate these. And so if anybody remembers what doing finite element modeling was in the early 2000s, you know that it took a long time. And so setting them up took a little bit of time, but then the actual simulations, especially if you're tying RF to mechanical, took forever. And so it was probably over a week, which doesn't seem that long, except we were pretty much had a lot of parameters we needed to tweak. Now, the MEMS were also interesting, and I mentioned that they had a foundry. Now, we were building our own MEMS, and these particular MEMS only needed 4 lithography steps in order to complete. So only 4. So you could get that done very quickly in basically a week. And so you could then, the mask plates that you were looking at could fit about 400 different MEMS variations on them. And if you stamp them across the wafer, you could get 40 samples of each one of those. So I came in and I'm looking at these modeling, and I'm very, very quickly realizing that I could fabricate these things faster than I can model them. And I could get very good data. I could get sample data, so I could actually rule into process variations and other things like that. And so I went to the lead on this and explained the situation that, yes, I could model them if they wanted me to, but this made absolutely no sense. And I very quickly went from a modeler to a tester. And so we fabricated these MEMS, and we could spit them out so fast, and we could iterate so quickly, just design, back of the envelope, look at the fab, test, and then iterate very, very, very quickly. And so that's what I'm going to focus on a little bit, is this type of mentality. And I want to point out that I think here, looking around the room, I am old space. I think I qualify as that. I am in that last bit of that. But that was an example of that particular type of mentality that existed in old space. And I don't think this rapid iteration thing is a product or of something that's necessarily started, in the 2000s, but something that's been around and existed for forever. We use it at different times. Sometimes we over-focus on the learning and the modeling and the simulation upfront work instead of the rapid iteration. But rapid iteration design has been around for forever, or at least since I started. So we're going to say that's forever. Okay. So I focused, and I think one of the things I just want to a little bit touch on is when we think about hardware development. When we think about hardware development, and again, sorry, you're all software, but I'm going to talk about hardware. I know nothing about software. So I know you need hardware for the software. That's what I know. So if you think about hardware development, a lot of times what we tend to get tripped up on when we see these large things being developed, or we think about government programs, and the ones that are really at the top of our mind when we think about the government or space going slow, and you're really thinking about a massive system, right? And you're thinking about, okay, how long does it take this massive system to exist? But systems are built with subsystems, and then you've got subsystems with units, units with modules, module with components, components with transistors, and then even transistors are built with material systems. And so I would argue you have multiple different areas and levels that you can do this rapid iteration at. So you can iterate at a very small level when you're looking at the material systems to design your transistors, and then you're designing your transistors and iterating that, and then you're moving at each level above and above and above. But if you're talking about a overall system that has never ever been built before, and you need fundamental research in order to make that system occur, you're talking about a very long development cycle in order to do the iterations at all those different levels. And so I think it's very important at least to introduce or think about the idea of when you're looking at rapid iteration, where do I really need that innovation to occur, and what type of system do I need to make those breakthroughs in? Because depending on the level, you're going to run into different challenges. The other thing is advances in manufacturing methods introduce another factor in the iterative process. So when we think about, I've been talking about, I would say, or at least my RF MEMS was something that hadn't necessarily been done before, or I would argue it had been demonstrated before, it just hadn't been demonstrated reliable. So I was looking at a design change in order to make it reliable, or a lot of times you're looking at manufacturing changes in order to make it more reproducible, more reliable, or just get higher performance. And so when you're introducing all of those things, those add time into your overall iterative process. So then when we talk about iterative engineering, we think about the overall process. Now, we see a lot of times that these programs or other types of development, they are very waterfallish. So you do your design, you do the test, and then you use, and it's super slow. And you think about iterative engineering, you design, manufacture, test, define, and you keep doing this overall loop. And in each one, you're reducing that overall time frame, specifically reducing the upfront design, manufacture, and test, and then moving quickly through each one of those sequentially. Um, However, I would also say that if you're looking at the product development, you also have to essentially insert all of those at the different levels. And so you're not necessarily just thinking about it in terms of a one component or a widget, or in my particular case right now, it's going to be an engine. So I'm not just looking at it, I'm looking at all the different levels and how to use it. When you're looking at the product development, it's really only available, and again, I point out launch, when you have the low cost and quick way to test your product in its final environment. So you can do a relevant environment. You guys all probably heard the TRL levels, great. But what you really want to know is, how does this work when I put it where it's supposed to be? And in many cases, and a lot of discussions happen around the fact that test is your final test bed. That's your real test bed for where you need these things to work. And you can only really do this with low cost access to space. There's a number of people who would love to see how systems work. They would love to see it in space. But the number one issue that they're running into is the launch is so expensive. I can't waste it, or it's so unreliable that I don't want to actually risk my system in order to do this. So they're pushing these systems to be more expensive and to only fly things after they've been proven, because it's just too expensive and too constrained to actually get them up there. And we see right now that there's a large shift in that. As we see more and more routine flights commercially, you could see the number of experiments that are occurring, the number of startups that are quickly putting things, fielding them in order to demonstrate them, doing their first experiment, getting data, and then iterating quickly. And the only way you can really do that is if you continue to have that access to space. And I just want to point out, I talked about this before, but again, when I'm talking about a launch system, we think about SpaceX and their philosophy, rapid iteration, rapid design. You're really looking at essentially being able to do that at the system where you're doing the innovation at. So if you're actually innovating at transistors or component levels, you need to keep pushing these downwards. And so in this particular case, I've added multiple kind of loops in order to really talk about the iterations that's occurring on the subsystem level. The other thing that you need to consider is your on-ramping. So a lot of times if you are doing a new system that is brand new, it's never been done before, you're going to want to do your requirements and then your sub allocation. And while you're doing that, you want to actually start start building as soon as possible, start building best guess to what the requirements are going to be, start iterating and beginning that process and feeding it down into the loop. A lot of times we think to ourselves, I don't want to start building until I know what I should be building. But you get so much information and so much value just from increasing, and I could do it. Don't feel guilty. I needed a walk. Um, so, uh, so you just want to make sure that you're actually having roadmaps for your new tech. So when you're thinking about um, your baseline, think about what can I do in order to speed learning at each individual level, and what can I do to bring in new tech. And so in my experience, when I talked about MEMS, we would have very large programs that honestly did things that no commercial assets could ever do. And so the plan to do that was to always use existing tech, build it and use existing tech, iterate at the lowest level and continue to do that, work on your sub allocation, and then come up again. I can't do it this way. And then rebalance your specs across the system and keep doing this iterative cycle. The risk comes in because you want to start using new tech and add new capabilities. And the way to really do that is use your baseline, get that established using low risk. But then at each point in time, as you're proving that new tech can work, you're on ramping them. You're bringing them up and then taking spec relief in those areas, and then keeping over and doing that process over and over again, as I mentioned. And again, when we think about launch, I'm going to pull it back to launch. The systems that you're looking at, although their impact, if they go wrong, is quite more dramatic. If you blow up an engine, it's a lot worse than if you blow up a circuit. They're still, we're innovating not necessarily at the subcomponent level, but we're innovating at the engine level. And so that's why you kind of see with SpaceX and some of these other things, you see them going faster and faster and faster, simply because they're not necessarily, or they're able to utilize pre-existing type technology. Okay, so how did we get to this point where we think to ourselves, with these very, very large systems, that we're not necessarily doing this iterative framework? And I would say a lot of it is perception, as I mentioned before. Again, old space, I use this framework for components. But I do think that one of the things that we all fall victim to is this minimum viable product mentality. What is the minimum thing I need in order to make this work? And what do I absolutely have to have? And when you're thinking about that, you want to think about as well schedule and cost. So is cost really the most important thing? Or is my performance the most important thing? Or is schedule? Do I have to just get it fielded? And this is a dramatic shift that you even start seeing with I would say organizations like the Space Development Agency, the SDA, in their tranched approach. They're really looking at using commercially existing technologies to get it going fast and get them deployed very, very low cost. And so they're not looking at absolutely maximizing their performance. They're looking at just getting things fielded in order to help with overall resiliency. So they're looking and they're keeping an eye on, my minimum viable product is this, but the most important requirement is my cost and my speed. So I'm going to focus on that. A lot of times what happens is when we did have an issue with getting access to space, you think to yourself, if I'm going to send something up there, it's got to work. And if I'm going to take this long, then I really need it to work. And if it's going to cost this much, oh my goodness, I need it to work even more. So you're looking at developing exquisite systems with incredible performance. And very quickly, you have this runaway effect. And the runaway effect starts actually being, I've spent this much time and money making this. It really has to work. I've spent this much time. Now it has to really be reliable. And all of a sudden, you just have this runaway type behavior where you can't fail. You have somehow reached the point that as you've started adding things on and on and on, you've essentially gotten to a point and can't fail. And then you, again, when you're talking about putting, you're putting something up there, people start adding capabilities. Well, I want this too. Well, if I'm going to pay this much, I want this as well. And very quickly, you're losing sight of the minimum viable product that was your overall requirement at the very beginning. So the next is you have misaligned incentives. And this, I mean, I think this goes across the board. Everybody understands misaligned incentives. But when, and I'm going to say something that's probably blasphemous at this point in time. However, I would say that if you look at your overall contract structure and you start talking about the way we basically, I would say the way we reward risk and how we talk about risk is actually misaligned to what we're thinking. So in a lot of cases, you have government type contracts that are cost plus. And I know that's a horrible, horrible, dirty word. But the main point of cost plus was simply to encourage people to take risks and to basically say, we will join you in your risk taking and please do it, contractor, because we want you to. Of course, it's been completely muddied since then, but that was the original idea. When we are forcing people into some of the more firm fixed price type things, what you are doing is you're basically saying you can't take risk. And you are unaware, you don't want to take risks. You want to move fast, you want to get up there, and you don't want to spend the fundamental time in order to understand it or develop new groundbreaking technologies. So, and I'm not necessarily one is terrible or the other is good. I'm just saying they're very useful in different cases, and you have to understand why you're using them and actually to align your overall incentives. So when you do force people to try and field new technologies and take on new types of things, you really, really need to encourage them and say, I'm asking you to do this, so please do this. The knowledge trap. And so this is one of the things that I find fascinating, because as you do more work and as you understand more and as your capabilities become better, you become very um, you become very excited about using that knowledge and putting in place using that knowledge in order to basically make your first time you build it successful. And so when I was around, we talked about first pass success, which I find absolutely crazy right now. But that was definitely a thing. It was, hey, we have all this information. We should be using it. We should be feeding it back into our simulations, and we should be using it to guide design and completely get it right before we build. And I would argue that that is a trap. You can always use more design. You can always continue to polish it, and you can always continue to push it. However, the fundamental learning you get when you actually do it faster cannot be replaced by the upfront learning. The other thing that you run into with this overall trap is that you look for, let's see, you look for ways, continually look for ways to uh, to feed back into it, and you get stuck with this idea that you're essentially siloed between your test and your design. And so you start developing people who are very good at one and not very good at the other. And then you like to see that, just if I'm designing, I don't want to necessarily send it to test too fast. Otherwise, I'd be throwing it over the fence. And so you start to see people who hold on to it and not necessarily collaborate with the group and consider the overall design and build and test to be the complete responsibility. And so you start to see these silos form. The other thing that happens with these knowledge traps is that you start to create, I did this once, it failed. I should create a process in order to stop this from happening in the future. And as soon as you start doing that, you start relying on that process and losing the institutional learning to why that process was there in the first place. And then you're completely reliant on that. And very quickly, you're left with people who don't remember why it was there, but only that if you don't do it, bad things happen. And so this you've seen kind of repeatedly at different kind of companies. They hire people with lots of experience, they bring it over, they institute the processes without any fundamental or institutional knowledge about why that process existed in the first place, and then they roll it out. And once you lose that knowledge about why they did it in the first place, all of a sudden you're stuck with not knowing when you can break the process. And processes are great because they help us. They're like checklists. But as soon as you start using them in a way that doesn't allow you to move around them, to change them, or other things like that, you're stuck. And it's very, very hard to break through that. So I would say that is, you almost have too much. You've lost the institutional knowledge that led you to really understanding what your system needed to do. So how do we do this right? So I think I have one more slide and then I get to cool pictures. So bear with me. How do we do this right? So obsess about the MVP and the most important requirements. So when I say this, it is so easy to get distracted from this. It is so incredibly easy. I see it across the board. Uh, you have one requirement and then all of these nice to haves start running in, and you think to yourself, what is the only thing I really need to accomplish? And very quickly it'd be like, yeah, but you know what? If I did this, it would save time. Or if I did this, it would save time. Or if I did this, it would make it better. No, always focus on the minimum viable product and your most important requirements, and never ever lose sight of that. The other thing is, be wary of your knowledge gap and keep learning. As I mentioned before, you learn so much from test. No matter what you're learning from design and how much modeling you put into it, and then feedback for measured versus models, there's always gaps. There's always problems with manufacturing. There's always process variation. There's always there's always going to be something that you don't know and you're not going to be able to capture. Keep an eye on that. Know that you need to get to test in order to do that. Keep small collaborative teams working across disciplines. So I think that is incredibly, incredibly important. One of the things that we focus on at Stoke is the idea that very quickly too large of a team becomes inefficient. So adding more people doesn't actually increase your productivity. It can very much decrease it. Getting people all aligned, keeping them marching, requires a lot of energy. So keep your teams as small as possible and make sure they're working collaboratively together, which means you're all working hand in hand. You're all owning the design. You're all owning the manufacturer. You're all owning the test, and you're continuing to do that. And then, of course, incentivize good behavior. That's honestly just a life thing. Yes, sure. Uh-huh.
Oh yeah,
Yeah,
sure.
I
So I
should.
was a bit curious about the knowledge traps that you brought up in the last slide, and I was wondering how you kind of avoid those from being generated inside of your projects and
Uh,
stuff like that.
Oh, no, sure. I would say, so there's a couple of knowledge traps that I mentioned. The first one would be with the process, and that one you're nodding your head, so I'm assuming that's what you're focused on. I would say process is always good if it's helping things be repeatable and if it's simply a checklist, right? When we're going someplace, we don't need a process to tell us how to pack, but certainly checklists are useful to remind us of what we may forgot, right? So always use them as, try and keep checklists, but make sure you're transferring that institutional knowledge about why those existed and what you're putting in place there. And so it is, I would say you always need to value the people who understand that and make sure that they are transferring that knowledge to the newer folks coming in. And a lot of times what you see is uh, you see the loss of that knowledge and then not the good mentorship or the training that comes into that. And I would say you cannot ever discount the amount of knowledge and that comes from overall experience and having done it before. You're welcome. So now I'm going to get to the cool pictures. Yeah. Thank you. So this is our rocket. It's called Nova. Uh, the first stage is Zenith, so it's our Zenith engine, and the second stage is Andromeda. So that is our. They're both fully reusable, and so number of different use cases that I mentioned before. But this is what we're working on building right now. When I talk about minimum viable product and actually keeping your focus, our focus right now is building a launch vehicle, and we're going to focus on building a launch vehicle. And so that's what we're working on. Okay. Chris showed a much better picture of our heat shield. So I love that. I think it looks like a turtle shell, but it's wonderful. So we have a reusable heat shield. So the story goes, we're going to call it myth, legend, goes that Andy and Tom are two co-founders, are engines folks, and they said, hey, how do we actually develop something that can withstand reentry? And they said the thermal environment during reentry is not as bad as the thermal environment inside a combustion chamber, and we regeneratively cool that. So why can't we do the same thing with the heat shield? And so they came up with the idea of cooling this. So we use hydrogen to cool it, and then hydrogen as well to fuel the engine. And so the hydrogen is cycled through the heat shield. We use an expander bleed cycle, and then it's used to spin the turbines and then used for the fuel as well. And so this is incredibly robust. I think somebody said that we could shoot it with a gun and nothing would happen. We haven't actually done that. So we haven't. However, we have dropped things on it. We have dropped hammers. We have the version of this that went on the hopper. We took off the hopper and continued to test for like 8 months longer. So it is incredibly robust. And then you have the engine kind of buried inside of it. It is far more ductile and requires far less maintenance than, say, your ceramic tiles. And it also has a passive failure mode, which means if it cracks, it's just going to overcool in that particular area, and you're not going to see some of the catastrophic type failures that we saw on the shuttle, or other things that use the heat shield, or the ceramic tiles for the heat shield. And this is the Andromeda engine with a heat shield. And so you can see the blue are the thrust chambers. So this particular version, this is the one that went on the hopper. This had 30 thrusters, and they were all individually throttable. Our new upgraded version has 24, and they're throttable in pairs, so we call them pods. And so we've replaced that. We've also buried those thrusters more in the heat shield itself, and it doesn't have that elbow that you see down there, which actually makes it much more difficult to take pictures, which who knew that was going to be our biggest problem with it right now. But you can't get these pretty pictures that you see here. But one of the things that I love about this picture is that you actually have frost forming on the heat shield in the fire right there. So that heat shield is so cold that there's frost while it's firing. And this is our Andromeda test stand. So this is at Moses Lake, so it's about 3 hours east of here. This was a huge, I would say, factor in our ability to move fast, having our test stand so close. One of the things that we regularly do is we send hardware there, and then we test it, and we immediately do a redesign or upgrade, and then drive it back out there. And so we have people going back and forth to Moses Lake pretty much daily. I've gone out there, and okay, so I don't get to participate very much in the technical, and it's sad. And so when they ask me to do something to help, I get very, very excited. And so at some point in time, they asked me to this is the first stage, but they asked me to bring back the oxygen turbo pump. And I have a Mazda CX-5, and I was very excited about this. And the CTO convinced me it was a great idea, and I was so excited. And I got out there, and they're like, Kelly, you cannot take that back. I said, why? And they're like, it requires a forklift. Like, we're not, it's going to destroy your car. And I felt so So sad. But yes, so I regularly go out there. They put things in my car, I bring them back. But that allows us to go very fast. So we can bring it out there, we could test it, we can understand what's going wrong. I would the flight software team here does, and the data team as well, Noah and David. Yes, see, they are doing an incredible job of actually helping us get the data, test like we fly, have the vehicle software on there that we're going to use when we're in flight, and actually verify it works, get the data back, and spin over and over and over again for to iterate. So this is the hopper test. This was incredibly exciting. So again, this was at the Moses Lake test stand. This is an example of a minimum viable product in all of its glory. Vertical takeoff, vertical launch. We used differential throttle for thrust vectoring, and we reduced scope. We were constantly reducing scope and pushing ourselves in order to get this off the ground and get going. We knew that whatever nice to haves on there, while it would be great and nice to have, the best thing we could do was actually test it, fly it, and then iterate. And so this was a wonderful vehicle to actually do that. It also allowed us to test all of our avionics packages, our software. It allowed us to test so many more things in an integrated fashion. And one of the things that you run into with testing is you're always going to be limited by how much you've been able to incorporate on there as far as integration. And one of the things you run into, at least from RF perspective, is things, when you put them together, things act weird. They never act exactly the same way. In my particular example, we did integrated microwave assemblies. We would put chips in there. No matter how much you simulated the chips and how much you did, you would always end up with either crazy mismatches that caused reflections or other types of modes or oscillations that were created that you never could model. And so the final getting it into and testing it and actually seeing if it would work was huge. You don't know how many times we used Echozorb in order to kill an oscillation because it randomly appeared. But yes, so testing integrated is huge. And this allowed us to do this. And then, as I mentioned, we tested that heat shield and then an overall engine. We took it off of the hopper, and then the hopper became this very large, I guess, monument in our manufacturing floor that everybody likes to see. But the engine went and continued testing for about 8 months more. And so this is our Zenith engine. It's a full flow stage combustion Methalox engine. And I will talk a little bit more about this. This we've been able to do incredibly fast as well. One of the things that we have at the Moses Lake test stand is actually component test cells. So we're regularly sending various parts of the engine out there in order to characterize them separately. And then we do the full integrated testing, but we're doing them all at the same time. So that test stand can not only test the engine, but at the same time, we could be testing components and different portions of that engine in order to do upgrades or other types of optimizations. So where do we build that? This is all done in Kent. So this is our manufacturing facility in Kent. We were in there. We've been in there about a year, but all of our manufacturing that we need to do is in there. We're incredibly vertically integrated, so we outsource very, very few things. Again, one of the things that we look at is when you're talking about, I'm going to keep saying this, but when you talk about rapid iteration, is being able to control it yourself and use the manufacturing and keep iterating on that. And so we've taken it very literally, and we have all of the things that we need to make we can do in this facility. And that's just another picture of it. So this is the Zenith test stand. This is where we do the vertical testing. Again, very much test like you fly. So everything is all the software and hardware that we would use to actually operate the engine is incorporated into the test stand as well in order to do the testing. And this is one of the neat features about this is that we have it at ground level in the back. So you could just drive up the engine, not using the Mazda, and put it inside in order to test. So this is again in Moses Lake. And with that in mind, with that, I guess, iterative process, we are the fastest company to go from seed to first engine test out of everybody. So this philosophy of iterating is, um, yeah, gets it done fast. The one thing I want to point out is, I we we are very, very blessed to be, I would say, a little bit kind of later than some of these companies, in the sense that we are utilizing a talent base that has grown substantially since I entered, I would say, the workforce. And so we are standing and utilizing expertise from across the industry for folks who have many, many, many years of experience. And that really kind of, the amount of talent really kind of took off, I would say, uh, in the 2010 kind of time frame. And so we are absolutely utilizing folks that have an insane amount of experience. So I just want to put it there. It's a little bit disingenuous not to mention how good the industry is at producing top talent. So one of the other things I wanted to kind of point out, the low cost access to space removes the orbit demonstration barrier. Again, one of the things that you see with new space in general, for startups, as well as you see the movement with the government, is this idea to actually test things on orbit, get them up there, verify they work, not do all this on ground testing, with the idea that if it doesn't work, and if I keep it low cost and it doesn't work, I could send something up there to replace it, and I don't have to worry about it. And that only comes if you have very good access to space and the launch cost is not prohibitive. So continuing to reduce that launch cost will actually help substantially in enabling people to move fast and continue this iterative philosophy. And then just a shout out, because it's kind of cool. So we do have a launch site at the Cape. So we've got the historic Pad 14, and we were the fastest company to be allocated a spot. And so that is moving incredibly fast as well. That is largely due to the talent base that we've pulled in there. But we're right between Relativity and the SpaceX landing zone. And so that is being worked on and activated right now. Okay. Any questions? Yes. Oh.
Hi, John Jorgensen, Blue Origin, software safety engineer. I just wanted to thank you for the presentation. Maybe just add to it some of the lessons that we have learned. The first thing is in safety, the stakes are a lot higher even than with the reliability and the property damage, of course. So that tends to make people sort of dial up the processes and exacerbates the problems you're talking about. But I think that we can still get more rapid iteration even with safety considerations. One of the papers that were very instrumental to us, set of papers, is by Robert Ocampo. We hired him as a software safety engineer. He did a lot of research, and then he currently works at Boeing, I believe. But I recommend going and reading that paper. Because what he did is he analyzed all the research, all the data that he could gather across all the safety industries as to the usage of a particular activity, like driving a car, flying an aircraft, going in a submarine, and he plotted that against the risk, the loss of life. And what he found was not just a tiny correlation, but a very strong correlation that the more the usage goes up, the more the safety risk goes down, which is very surprising because one would hope that as a safety engineer that we're doing some good work. But if all it takes is to increase the usage to get the safety risk down, that kind of calls into question, what are we doing here? Now, he didn't talk about the causes for that. So presumably the causal relationship between the usage and the risk is because safety engineering exists. But it highlights the importance of getting high usage. So that's substantiating what you're saying. But other things that I think we can do and that we've been learning at Blue Origin related to getting the risk down with better, closer iterations. Certainly we're watching all of our partners out there in the world. One thing is we have to realize first that we have to build the safety in. We can't just design it, or sorry, we can't just test it in. So this is a mantra in safety engineering that you can't verify the safety in, you got to build it in. That seems to go counter to the idea of rapid iteration. But I think we can get earlier unmanned vehicles that will help buy that risk down, willing to take on risk with the loss of property, the loss of mission, before we have to put people on it. Other things is that we can put some of the technology we're going to be using in crewed missions. We can incorporate that into earlier unmanned missions, maybe even earlier products, so we get experience with it. An example of Blue Origin would be our hydrogen oxygen engine that we got more experience with our New Shepard, but now we're going to be reusing with our lunar module. But more importantly, in terms of software engineering, I've done a lot of work, and we've been doing a lot of work at Blue Origin to understand which parts of the process matter the most. So I'm currently involved in the ASTM committee to develop the industry's software safety standard, working with NASA, FAA, and Space Force. And what we're doing, one of the things that I'm teaching the engineers internal to Blue, is that not all activities are equal in terms of buying down the risk. In fact, the validation aspect is more important than anything else we could do other than config management. So I tell the engineers, if you're going to put your early money into buying down the risk the most, the first thing you can get done right is config management. The second thing you can get done right is validation. So early validation, very tight iteration on the requirement side, the design side, get that early. And then later you can push things like code reviews, and you can push things like a lot of low-level unit testing, push that till later. Structural coverage analysis can be pushed till later. So this high iteration, enabling that while buying down the risk with the best use of dollars, config management validation is the best. So those are some ideas.
Oh, no, thank you. I appreciate that. Yeah, and certainly we don't want to iterate with safety. I think, yes. Any other questions? Yes.
Can you pass the mic?
Sorry, I had another question. So I'm a bit curious. So we have a CubeSat that we're trying to build, and we're pretty broke. So I was wondering how you balance like iteration, because you have to buy all these things and everything, and then you fail and so on and so forth. But how do you balance the amount of iteration cycles you do on subcomponents and the big component versus like time and cost and stuff like that? Because I mean, I'm also a student. I don't really know much about managing timelines. But yeah.
So your question is, how do you iterate on the subcomponents?
Well, I guess how do you iterate on any component that you have in a cost-effective manner, and how do you balance
How
your
do you
cycles?
balance that? I would say in most cases, and I'm trying to bring a good corollary up into my head. I would say in most cases, is that component you're iterating on 100% necessary in order to accomplish what you need to accomplish? And so, so if it is, then I would say it's fundamental to the mission itself. It's one of the overall. It fits into your minimum viable product, right? Whatever you're doing, it has to be on there, right? You can't descope it. You have to keep it on there. And so, I would say if you are a student, then I'm going to assume as well that when you're talking about cost, you're not talking about man hours. You're simply talking about hardware itself, correct?
Yeah.
Okay. And so the best way to do that is the best way I've done that in the past is I continue to build the baseline, and I break off little tiny tests that I can do that aren't necessarily the exact hardware that I'm going to do, but I simplify it into something that's cost effective that gives me the data and the analysis of things that I need. And so we would do this regularly on this other program that wasn't using MEMS, but it was a very compact phased array. We had to figure out how to actually integrate it and get the elements kind of smushed onto one particular board. And the way that we did it is we had a baseline. This is what we need to do. We assumed it was going to work. And then inside that, we did in parallel concurrently. We broke it off into very small little experiments that would either verify or help us iterate on it. And we kept that in mind so that when we would come to that particular step, we could easily on-ramp that. And that was simply identifying, this is exactly what I'm going to build, and these are the points of no going back, right? These are the time I have to have an answer. So what concurrent learning can I do, and how can I break it down into very cost effective type areas? And in some cases, what we did do is the main risk with using a particular chip, because we were stacking chips on top of chips and it was just crazy. And so what we did do is we said, okay, this particular chip is really expensive, but I can get this other one that is kind of the same, and I can verify that that works in this configuration. And it's a tenth the cost. And so we would look at kind of cheats that way in order to buy down the risk. You're never going to buy it down completely, but in order to get enough confidence that we can move forward.
Gotcha. Thank you.
You're welcome. Any other questions? Yes.
We have a question online, then we can go to in person. So a question from Brian Kempa. Do you have any personal rules of thumb for taking advantage of experience without falling into the knowledge trap, especially on smaller cross-disciplinary teams where it can be more difficult to know how and what to challenge?
Oh, it can be more difficult. I would say I've been far more often the challenger rather than the challenged. I would say if you're the lead, I would say I think it's important to always be able to accept challenges and to always listen to it and to always allow folks to dive in and understand the exact reason why you are doing things and to continue to push. And if you don't really have a good answer to why, you should continue in that question. Unless, of course, it's distraction. It doesn't actually provide any kind of benefit to like the overall schedule. Sometimes when you go on a when you start questioning things and challenging things, that itself can be a distraction because you're challenging everything as opposed to the things that really, really matter for your overall timeline. And so I would say focus on those types of things, encourage people to challenge them, and join them in finding out why, and to continue to just kind of let that happen. Most of the time when people are challenging things, they're not being contrary, they're not being trying to be annoying, they really just want to learn. And so teach, and even if you're not necessarily even if there's not really a good reason not to do the process, still it's an excellent time to teach them why that exists in the first place, so you can continue that kind of knowledge transfer. So I would say that. Or I think one of my biggest things that I've always done and I always enjoy doing is to ask the team as you're sitting there, what are we missing? What am I missing, guys? What have I left out? Like, what assumptions have I made or you made, or, what are we missing? Because I'm certain we're missing something because it seems too easy. And usually just kind of being paranoid in that way. I forget who said it, but only the paranoid survive. Right. But being paranoid in that way that you're always inherently missing something and you needed to continue to kind of look for those kind of traps, I would say, even as you're pushing things, is incredibly helpful.
Thank you. Yes, we can do one more.
Thank you for giving the presentation to us. It was really informative, super interesting. My question to you, you talked about iterating. Can you share a little bit about any lessons learned trying to reconcile supply chain challenges? Because you're trying to move fast, but sometimes supply chain issues just don't really work with you. So maybe any thoughts on that topic?
Oh, I have so many. Oh, okay. I would say, I will tell. I will tell. I think two kind of big ones. The first one was in one of my programs, I was again creating a process for stacking chips, and I needed to develop a process to create something called through silicon vias, right? And so most And a via is essentially when you're talking about an RF chip. You have ground. The ground is on the backside, and most of the time, in my particular case, I was using microstrip. I was using a microstrip mode for the transmission line, and to be able to do that, you actually have to tie the top and grounds together, because in RF land at high frequencies, ground isn't always ground, and you need to make sure that you kind of keep that consistent. And so I needed these to actually occur in vias. I needed these vias to occur in silicon as opposed to what I was using, which was 3,5 semiconductors, which is like indium phosphide, gallium nitride, things like that. And so I had to put them in the silicon. And so I used an outside vendor in order to try and help me put those in the silicon. And I would say in that particular case, it was, I required daily updates with them. And I was an absolute pain in the ass because I just kept every single day, where are you? What have you seen? And kind of forcing the overall mentality onto them and, just really kind of pushing at them in order to make sure I understood their risk and they were kind of following that particular, our particular philosophy and buying down risk kind of at every turn. They weren't naturally going to do this. They very much wanted to treat us like a customer. We were a customer, but they wanted to be hands off. And so I had to really push in order to get them to do that. And that definitely, that was tough. And it just required a lot of oversight and active, I would say, just active in their meetings as well. I've dealt with another supplier. And in this particular case, this was an example of a R&D type capability that enabled a mission, and nobody tracked whether they could meet the volume that was needed in order to meet the customer milestone. And all we knew is that they could do it, and they could do it in very small volume. But it wasn't discovered until a milestone was on the line. And so in that particular case, again, it took very, very close, I would say, supplier management in order to do that. But in each case, the one thing I've learned is if you can do it in-house, do it in-house. That probably didn't answer your question at all because you're still looking at me funny. Sorry. Was that close?
It was exactly where I was looking for.
Yeah. Yeah. I would say yes. If you can't do it yourself, you are always at the mercy of suppliers. The one thing that you can do is in some cases, I've gotten suppliers to give me test coupons early on, so I can iterate with that. And I've gotten them to kind of simplify their process and what can you give me early? That's been helpful. But in general, it's very difficult to iterate with suppliers who are slow.
We have one more question online by Leor Atias. Hopefully I'll pronounce correctly. Can you share an example of a process you found to be overhead that you eliminated for the good of the project?
Oh. Yes. Let's see here. I'm going to have to go back to a supplier one because that was. I'm going to go back to suppliers. I would say one of the things that I don't know of anybody who has worked for the large corporation that has supply chain, but if you have, you will probably feel my pain and agree that there's probably nothing more frustrating in the world than being in an R&D project and having a supply chain tell you that you can't work with a vendor or that you have to wait for them to place your PO. And so that absolutely continually would slow me down in many, many different jobs that I had. And so one of the things that we quickly put in place was, in order to iterate fast, you have to have your parts, and you're not going to. And as you said, you can't make every single part in-house. There's just going to be things that you're not making in-house. And so the ability, if you're doing R&D and you're in the development cycle and you're not quite at the flight level, so you're not flying the hardware, all you're doing is iterating and testing to see if it works, and understanding that, hey, I need this from the fastest person who can provide it to me. I will understand the deltas to what I actually need to build, but the initial learning is going to be awesome. And so in that particular case, we removed all of the sign-off processes that required us to actually utilize kind of the supply chain overall PO placement, and allowed folks to, when appropriate, utilize their credit cards in order to place the POs quickly and allow the engineers to immediately get hardware as fast as possible. And so I would say that as long as you're following all legal aspects, so we don't want to buy from sanctioned countries or anything else like that, and as long as you're doing that, allowing your engineers to actually get access to the hardware as soon as possible is critical. And I think a lot of times what had been put in place was hardware that was development had snuck its way onto a flight product. And so in order to avoid that, they basically said, okay, then we're never, ever going to buy those parts in order to stop them from inadvertently get put on. And so in this particular case, we basically said, no, we need to put something in place that stops parts from using. However, in development, it's much faster and it's much cheaper. And I get the information I need in order to iterate quickly. So how can we get that into the engineer's hands as quickly as possible? And so we removed that overall cycle time and immediately allowed them to place part orders on credit card as quickly as possible.
Are there any more questions? One more? We can take one more.
Sorry to keep peppering you with questions,
No,
but great talk. Thanks for giving it. I'm kind of curious from your perspective, what it looks like when your software engineering team comes to you and says, hey, there's a new framework we want to try out. There's a new language we want to try out. And they ask for time to do a trade study and so on. I'm curious if you can see the return on investment on that, or if it's more, okay, software folks want several months to look into this and then they deliver a product, that works hopefully, but maybe it's less clear what all that effort was for. I'm just curious from high level what that ends up looking like.
So from a high level, what it looks like is, and I'm laughing because I think Chris did this to us. I don't know, very recently. I would say this. The one thing I've learned is you have to trust your team, and you absolutely have to trust your team. And all the things I talked about is assuming that you have an incredibly healthy team dynamic and group, and that everybody is taking personal accountability and owns all of their products. And you've been correct in adequately flowing down what the minimum viable product looks like, and you are constantly kind of communicating with them. And once you've done that communication and you have good people that you trust on your team, and if you don't have good people you trust, they shouldn't be on your team, but you have good people and you absolutely trust them. And I would say that is absolutely critical, because then if the software engineers come to me and they say, I want to make this change, it's really important. I say, I trust you. Let's go. And what do you need in order to get it done?
Thank you so much. Give it up for Kelly.